All right, let's jump straight into this explainer and crack the case of the seemingly chaotic output generated by a Haskell build directory. I mean, if you're a developer, you absolutely know the feeling, right? You hit that build command and suddenly, boom, a mountain of files appears out of nowhere. Well, today we're going to look at exactly what is happening under the hood when you do that in Haskell. We're specifically zeroing in on the often misunderstood dist-newstyle directory and all those GHC compiler artifacts hiding inside it. If you've ever compiled a pet Haskell project, like the Exes to ebook project we're exploring from our source material today, you've probably asked yourself this exact question. You write some really clean, elegant code, you run your build command, and then you take a peek inside the directory that gets generated. And honestly, what you find usually doesn't look clean or elegant at first glance. It kind of looks like a maze. You run a build, and you are just staring at this massive, overwhelming tree of obscure files and folders. You've got folders for your architecture, like x64-Linux, folders for specific compiler versions like GHC 9.10.3 and GHC 9.12.2, and then this seemingly endless list of files attached to your project components. You see things like paths_xs2book, CLI, converter, parser, main, all just repeated over and over with these strange different extensions. To put that into perspective, the single build for that simple X2 to ebook pet project generated exactly 59 directories and 119 individual files. Literally 119 files for a basic project. That is a massive footprint. It's totally enough to make anyone wonder, is this just pure clutter, or is there actually a method to this madness? So Section 1, why call it newstyle? The evolution of the build directory. Before we investigate those 119 specific files, we really have to solve the first mystery of our explainer. Why is this massive folder called dist-newstyle in the first place? Like, what happened to the old style? Well, to understand it, we have to look backward. In the past, the legacy format was simply called the dist directory, but it had a fatal flaw. It struggled heavily to handle multiple configurations across different compiler versions at the same time. If you updated your dependencies or just swapped your GHC compiler version, you were in trouble. You'd have to run a command called Cabal clean and literally rebuild the whole shebang from scratch just to dodge conflicts. The dist-newstyle directory was engineered specifically as the successor to solve that exact headache. It handles multiple configurations simultaneously without a single hitch. No more nuking your entire build just because you changed a version. Which brings us to Section 2, decoding compiler artifacts, making sense of the file extensions. Now, what's really fascinating about this directory is the specific compiler artifacts it generates. All those repeating file names with different endings, they actually aren't duplicates at all. They are highly specialized pieces of the compilation puzzle. First up is the .hi file. This stands for the Haskell interface file. It serves as a static interface holding absolutely crucial metadata for your modules. Think of it like a blueprint. It contains the types, the functions, and the structural info that other parts of your program might need to know about to interact with that specific module properly. Then we have the .o file. This is your object file. So while the interface file holds the metadata, the .o file contains the actual, heavy-lifting, compiled machine code. We're talking about the raw logic translated into instructions the computer can execute, specifically packaged up and intended for static linking. But wait, if you looked closely at that massive directory tree from earlier, you probably noticed it's also packed with files starting with the prefix dyn _. So why the duplication? Well, because by default, the Haskell project is actually configured to compile for both static and dynamic linking simultaneously. That dyn _ prefix literally just denotes dynamic. Which means, just like before, we have a dynamic interface file, the .dyn _ hi file. It does the exact same job as a static interface file, providing the structural metadata, the types, the functions, but this one is specifically tailored and meant for dynamic linking instead of static. And naturally, its partner is the dynamic object file, or .dyn _ o. This is the compiled object code designed specifically for dynamic libraries. If you're used to seeing .so files on Linux or .dll files on Windows, well, this dynamic object file is exactly what goes into building those shared libraries. Okay, so how does this build process actually look in practice? Step 1, the compiler generates the static pairs. Step 2, it simultaneously generates the dynamic pairs. And the absolute beauty of this parallel process is Step 3. Your final executable binary now has ultimate flexibility. Because the compiler generated both sets of artifacts right out of the gate,
Your program can be linked either statically or dynamically depending on what you need, without you ever having to go back and recompile the whole thing.
And utilizing these dynamic versions is incredibly powerful for a few key reasons. First off, it allows you to build executables using shared libraries. Because you're sharing code rather than baking it all into one giant file, you significantly reduce your final binary size. But perhaps most importantly, it lets you update your dependencies without triggering a complete, agonizing recompilation of your entire project.
Moving on to Section 3, the mastermind design, the secret to incremental builds.
So here's the crucial takeaway. This giant, messy directory with its 119 files, it isn't just chaos, and it isn't poor cleanup by the compiler. It is actually a masterclass in software engineering architecture. The sheer volume of files is exactly what enables the system to be so blazingly fast and adaptable. Here is the absolute aha moment from our source text. All of these files we just decoded collectively act as a content-addressable cache. If you aren't familiar with that term, it functions almost exactly like a checksum for your files. The system isn't just blindly looking at file names or modification dates, it's looking at the unique mathematical fingerprint of the actual content inside the modules.
What does this mean for us? It means that if you go into your code and tweak just one single module, Cabal, the Haskell build system, uses this incredibly precise content-addressable cache to ensure that only the specific modules affected by your change get recompiled. It skips everything else. This right here is the secret sauce behind highly efficient, lightning-fast incremental builds. It uses that massive, supposedly messy directory as a meticulous filing system to save you tons of time on every single subsequent build. I really hope this explainer helps you appreciate the brilliant mechanics hiding right behind your build tools, because what looks like an overwhelming dump of obscure files is actually a perfectly organized, content-addressed cache designed to make your development life infinitely smoother. So I'll leave you with this. The next time you trigger a build in your favorite language, what other brilliant, elegant systems are hiding their solutions right there in plain sight?